Hello, everyone, and thank you for joining us today. Welcome to our latest Tech Talk webinar, Paving the Way for Efficient High-Density AI at 400G and 800G speeds. We're excited to continue exploring the latest trends and innovations shaping the data center and network infrastructure landscape with you. I'm Brian Baum, Corporate Marketing and Communications Manager at Siemon, and I'm excited to be joined by Ryan Harris, Siemens Director of Systems Engineering and High-Speed Cable Assemblies Expert. As always with the Siemon Tech Talk, if you have any questions during the session, please enter them into the GoToWebinar interface, which you should see on your desktop screens. We'll have a short Q&A session at the end of today's webinar to address any questions that get submitted. Okay, Ryan, over to you.
Hey, Brian, thanks for the introduction. And also thanks everybody for joining. Today, I'll be presenting efficient high density 800 gig and 400 gig network cabling options. So this webinar is split into three sections, starting with network connection points, and then AI network cabling considerations, and then we're going to end with cabling options that improve efficiency. In the middle of sections 2 and 3, we're going to have an interactive survey poll where the audience can participate, and we're going to be sharing the results live for all of us to know where we're at with high-speed deployments today. And it starts with AI network connection points. So generative AI is being used as a strategic advantage across various industries. For example, the left shows AI use cases, for example, knowledge management and search, virtual assistants, content generation, data image and video analytics being used across industries like communications and banking and manufacturing, healthcare, government, and retail. For this reason, the AI backend deployments are a fast-growing part of the Ethernet data center network, as shown on the right. So you see this red line. The bottom part is the fast-growing backend network, and the top part is the front-end network. There are two different data center networks that connect to each other. There's the traditional front-end network on the left and the growing back-end network on the right. These networks are typically connected via a hybrid approach using both on-premise and cloud for scalability. The front end on the left supports mobile apps, website hosting, e-commerce websites, cloud data storage, and more. And the back end on the right is processing intensive for model training and high performance computing. Inside the backend network are two different focal points to increase performance. The scale out network on the left, where every server has a network interface card that attaches to a leaf switch, that attaches to a spine switch, where there's rows and pods connecting together to make a cluster and using protocols like Ethernet or InfiniBand. On the right is showing new emerging scale-up designs for GPU to GPU connectivity. This is where the entire racks or the entire rack of GPU shares resources and communicates like a single server. New industry standards like UA-Link and CXL are competing with NVIDIA NVL72 rack systems that have scale-up connectivity. Today, we're going to be focusing on the scale-out connections on the left. So 800 gig is being deployed in volume, proving to be a great choice for scale-out. The graph on the left shows 800 gig switch port speeds in blue as the most popular, forecasted out to 2030. So you see there's 800 gig in the blue, 400 gig in the orange, and 1.6 terabytes in the green. And again, the blue line is the most popular out to 2030. The right side shows 800 gig enterprise forecasted in blue, ramping out all the way to 2030. The orange line shows the cloud, and so cloud service providers are using 800 gig the most today, but enterprise is ramping and using 800 gig all the way out to 2030. These details were collected across multiple sources to show how popular 800 gig connectivity is not only today, but also in the future. There's 4 building blocks to any AI backend network. There's the GPU network that connects at speeds at 400 and 800 gigs. There's the storage network that connects at speeds from 100 to 400 gig. There's the front end network that also connects at speeds at 100 and 400 gig. And then there's the out-of-band network that connects at 1 gig speeds. All 4 are connected using the network equipment shown on the right. And today we're going to be covering efficient cabling options for the GPU network. So as shown by the red arrow. So that was the first section. And there's lots of different reference designs from NVIDIA, Cisco, Dell, and many of the storage OEMs. And so next I'm going to be reviewing some cabling considerations to improve efficiency with those reference designs. GPU server nodes require a lot of power, which is shown in that gray box on the right. It shows a node drawing approximately 8.4 kW just on a single server, and how much power you can support in a cabinet determines how the system is laid out. For example, if you can support 20 kW in a cabinet, that would be 2 nodes per cabinet. And if you wanted to deploy 128 GPUs or 16 nodes, you'd have to divide it out over a floor space or multiple cabinets. If you can support 40 kW using a rear door chillers, you could put more nodes inside of a cabinet. For example, 4 nodes, and that enables you to deploy 256 GPUs or 32 nodes in the same footprint layout as shown above, so higher density. There are some high power data centers that can support 100 kW per rack, and the racks are typically liquid to chip cooled with approximately 8 nodes per cabinet, where you're getting that same 32 nodes or 256 GPUs in a much smaller footprint. So there's more than one way to route cables across AI systems and cabinets. The left shows horizontal routing, which is a more direct path than vertical routing shown on the right, meaning it's a longer distance to go up and over than through the middle. As you can see, the left is horizontal and the right is vertical routing. And this is important because minimizing routing paths provide more options for cabling types. At the top of this slide, it's showing cabling options and the length supported. So the blue is showing copper cables out to 5 meters. The purple is showing AOCs that can support up to 30 meters or above, typically inside of a row is recommended. And there's also the orange, which is structured cabling that supports 50 meters or above, which is great for basically routing across rows. Using vertical routing at the top example, 800 gig copper cables can make a connection across 2 adjacent cabinets, as shown in the blue. However, when using horizontal routing, copper cables can make a connection across 4 adjacent cabinets. You can see it's more of a direct path as shown below. This makes it possible to use 800 gig copper cables to connect many GPUs. Cable flexibility is important for cable management. The left shows the bend radius of fiber versus copper. The smaller the number, the more flexible. So it's showing that fiber using OM3 fiber has a bend radius of a little less than an inch. Then there's copper cable. 800 gig copper usually has 2 dual cables out of the back of the housing, and it has a much larger bend radius of 2.8 inches. However, there's been a lot of innovation in copper cables where there's a new mesh cable construction, and with this new mesh cable construction, it gets the bend radius around the same as fiber, as shown below. The right is showing routing paths with multiple bends, and this is important because bending cables outside of specification can cause flapping and performance issues, and so every bend counts basically when routing and dressing cables, and they add up. There's lots of bends. Because AI GPU connections are high density, the cable outer diameter and bundled outer diameter are very important. Again, the left shows the outer diameter of fiber versus copper. So it's showing that fiber at the top, OM3, has an outer diameter, and these are worst case numbers, of 3 millimeter. And then the dual copper, again, worst case, 26 gauge, which is really thick, has an outer diameter of a single cable, again, dual cables, of 19.6 millimeters. And then there's the new mesh design that has an outer diameter of 12 millimeters. And this is 38% smaller than the typical copper cable with this new design. The right side shows 32 mesh cables bundled together for high density routing. And so the graphic shows 32 cables and the outer diameter is 72 millimeters. And 72 millimeters is enough to fit through a typical cabinet cutout with the width of 99 millimeters. So this shows how copper can be used for high density routing, either horizontally or even vertically through the same cutouts. Also, because of high density, power and heat are very important. The left shows 800 gig power, so using standard transceivers with digital signal processors, it's approximately 14 watts per port, compared to LPO, low power optics, that get all the way down to 5 watts per port. Then there's copper below that, where the AEC is approximately 8 watts per port, the ACC is 1.5 watts per port, and the DAC, the passive DAC, is just 0.1 watts, and it's by far the lowest power option. And it's the same on the right with 400 gig, where there's DSP optics that have the digital signal processor, are higher power than the LPO versions that do not have the DSP inside the transceiver. They get all the way down to 3.5 watts. Then there's the AEC below that, that's at 4 watts. And the ACC is lower than that, and the DAC is by far the lowest. Power is important for saving in cost in cooling, and then also powering up your system, but it also reduces heat in your system as well, which is just as important. Price also plays a big factor in making an efficient cabling decision. For example, on the left, starting with fiber cable assemblies, and a fiber assembly is basically 2 transceivers and 2 MPO or MTP fiber cables. The 800 gig transceivers typically have dual MTP connectors, but you compare that to an AOC, the AOC is approximately 10% less. And then next would be the AEC that has a retimer chip, and that's approximately 25% less than the transceiver assembly. And then next would be the ACC that has a redriver chip that amplifies the copper signal, right? That's 60% less than the transceiver assembly. And then at the very bottom is the passive DAC, and the DAC is approximately 85% less than the transceiver assembly, making it by far the lowest price option. So at this point, we've gone over a lot of cabling considerations. I know there's others, but these are some important ones, again, that add up quickly in high density systems. So at this point, I'm going to be passing it off to Brian, where we're going to have an interactive poll, and we're going to share the results live.
Thanks, Ryan. Yep, so everyone should be seeing a poll question on their GoToWebinar interface right now. And our first poll question is, what server, NIC or HCA speeds do you plan to deploy in the next 5 years? Options include 25G server ports, 50G server ports, 100G server ports, 200G server ports, and then last 400G and 800G server ports. So we'll just pause a brief moment and let folks submit their answers.
Thanks, Brian.
No problem. Just a couple more seconds.
Still got some answers. I can't see it, so look forward to hearing the results.
Yeah, we'll give folks another couple seconds here. I think they're starting to slow down. So, all right, I'll end and share the results here. So it looks like we've got 12% response on the 25G server ports option. We had a 4% response on the 50G, 28% response on the 100G server ports option, 4% on the 200G, and then 52% on the 400G to 800G server ports.
Oh, wow. That's very interesting. I was expecting most of it to be at 100 gig, but it sounds like 400 gig and 800 gig are again happening today.
Yeah. Awesome. So everyone should see the next poll up on their screens. So that next poll is, when do you plan to deploy 400G and 800G switches? The options include 400G in the next 3 to 5 years. Next is 800G within the next 3 to 5 years. And then another option is planning beyond 1.6T. And then the final option, no plans to deploy above 200G. So just pause another brief moment to let answers come in. As I can see, they're still coming in. Okay, I think we're starting to slow down here. All right, I'll end and share the results with you right here, Rai. Okay, so it looks like we had 38% respond to the 400G within the next 3 to 5 years. We had a 24% response on the 800G next 3 to 5 years, 14% on the planning beyond 1.6T, and then 24% on no plans to deploy above 200G.
Wow, I'm kind of surprised to hear the number of 1.6 terabytes. That's definitely really high speed. So, but I'm not surprised to hear about the 400 and 800 gig. It sounds like they're the most popular.
Yeah. Very good. I closed out the polls, so it's back over to you, Ryan.
All right, thank you. So we've been going through this really quickly, and we're already at the last section, which is cabling options that improve efficiency. So the most efficient cabling approach for GPU to leaf connections is designing systems with horizontal routing using copper cables. The benefits of horizontal routing reduces the length between connection points, which makes copper an option for connecting adjacent cabinets. So horizontal routing is widely used across hyperscale deployments to improve efficiency. For example, OCP, the Open Compute Project, is currently working on a reference design promoting horizontal routing as a best practice, and it'll be published before the OCP Global Summit in 2 weeks. If you have any problems finding that reference design, just reach out. Also, using mesh copper cables that have a reduced outer diameter and improved flexibility, basically enabling the lowest power and lowest price copper cabling in high density deployments. For the leaf to spine connections, using structured fiber with patch panels for connections across racks, with low loss bundled trunks in combination with LPO optics is the most efficient cabling approach. This approach, again, for the leaf to spine, improves deployability, serviceability, and also reduces the power consumption in high volume switch-to-switch connections. The image on the below shows an example of using 2 patch panel connections. So there's a jumper to a patch panel, and then there's the trunk in the middle, and then another patch panel and another jumper cable connecting to the transceivers on each side. Using efficient cabling options has significant advantages. So the left shows the typical reference design where there's DR optics with digital signal processors being used for the leaf and spine connections, and also those same transceivers being used for the GPU to leaf switch connections. And so just across, 1,024 GPUs, you're drawing approximately 52,000 watts just in the optics alone. Compared to the right, using the efficient cabling approach that has LPO optics for the leaf and spine connections and copper for the GPU to leaf switch connections, you significantly reduce the power by approximately 64%, which brings 52,000 watts all the way down to 18.5 kW. And this adds up quickly because if you're deploying 2,000 watts, which is shown on the bottom right, or 2,000 GPUs, sorry, you're deploying 2,000 GPUs, the difference is 68,000 watts. Over 3,000 GPUs, you're all the way up to 100,000 watts being saved with an efficient cabling approach. 4,000 GPUs is now you're getting up to 136,000 watts being saved just by using efficient cabling. And this is important because we have lots of customers that are trying to deploy thousands and thousands of GPUs. And again, efficient cabling can not only help with saving power, but also efficient cabling can significantly lower overall price and improve performance. For example, copper cables have the lowest latency, and also using LPO optics that have the DSP or the digital signal processor removed also have the lowest latency. So you're improving performance at the same time. So the future beyond 800 gig is still deploying efficient cabling options. For example, DACs can still go up, or copper cables, DACs and active copper can still go up to 1.6 terabytes. Pluggable optic transceivers and AOCs can support 1.6 terabytes and beyond. And then there's new emerging technologies like co-packaged optics using optical switches and fiber jumper cables that are supporting speeds of 1.6 terabytes and beyond. Efficient cabling is all about utilizing a combination of connectivity types to reduce power, price, and improve efficiency, ultimately improving total cost of ownership. The Siemon company has a comprehensive product mix covering everything we reviewed and more. For example, pre-terminated bundle assemblies, high-speed copper and fiber cable assemblies, easy-to-use push-pull blade patch connectors, skinny cat cables that are great for out-of-band connections, high-density patch panels, and also economical patching solutions. In addition to products, Siemon offers quick ship programs, for example, short lead times because nobody wants to wait for a cable. Siemon also offers design services and also global account services to help in deploying globally. And we have a global footprint of hubs and factories and sales to help wherever you're deploying your products or your data center. Siemon is a partner with leading network equipment providers like Arista, Dell, and NVIDIA. Actually, in the next couple weeks, Siemon will be demonstrating efficient LPO optics with Dell and Keysight at the OCP Global Summit. So if you're in town, stop by. Siemon also participates with industry standards like Ethernet, InfiniBand, and Rocky, which is RDMA over converged Ethernet, really popular for AI connections. And this is basically with these industry standards, we do proactive performance and interoperability testing to ensure the best user experience. So this is my last slide. So thank you for listening. Please let me know if you have any questions.
Nice. Thank you, Ryan. Yes, we actually did have
Hopefully,
a
sorry.
num Yeah, no, just we did have a few questions submitted, and so right now there's four. I'll just
Okay.
throw the first one at you here. So first one submitted was, how is the horizontal cabling routed? Is it in the front or rear of the cabinets? And if cabling is routed across the front, does that not block equipment and paths for install and deinstalls?
So that's a great question. It's typically routed in the front, and that depends on the server, right? It's routed in the front. And then there's the cutouts that I was showing, and the cutouts have that size, the 99 millimeters, and you have to divide out the cables. And with the air-cooled systems or even the 40 kW systems, the servers, the rack's not fully populated, basically. The servers are spread out in such a way that there's room to route the cables horizontally. And there's also cable managers that can be used as well. Typically, the most difficult part you'll need to overcome is getting the connectors through the cutouts. But if you were to bundle, say I showed 32 cables bundled together, but if you were to reduce the bundles to 8 cables and then wrap those all together, you could put it in 8 cables at a time. And so 8 cables would go to each cabinet. And ultimately, there's one cutout that will have all 32 cables going through it, but it does go through, and it is widely used again with the hyperscalers because they want to use copper for the reasons that I was detailing with low power and low price. And every cabinet is different, every server is different. Some have the ports on the front, some have the ports on the back. And so basically, if you have a specific design, you can reach out to your local Siemens salesperson, and we can work out a solution for your specific data center needs. I hope that answers the question.
Thank you, Ryan. Yes, absolutely. So we did have another question just submitted just now. It says, does the networking options make a big difference in power and cooling considerations for a server that may have, for example, 4 times B200 servers? Wouldn't the 32 GPUs be the bulk of the cooling / power? And so networking is negligible for the total power / cooling conversation. That's the question.
Okay, so wherever you can, reduce power and reduce price, it's always it does add up. So when we're talking about just 32 servers, it probably doesn't make sense. But when we're getting into thousands and thousands of GPU connections, it does add up. And adds up again just in an initial upfront cost, but also operational costs as well. And ultimately, what you're doing is you're saving power, and it does add up. So hopefully that answers the question. But it has to be a larger deployment. And so it probably doesn't make sense, and it's not negligible to answer the question on just a few connections, but when we're focusing on the GPU connections, which is high density and high volume, it does add up.
Excellent. Thanks, Ryan. Just 3 more questions here. Next one was, does Siemon have transceivers and LPO transceivers?
So today we have DACs and AOCs, but we're also launching transceivers, both with DSPs and also LPOs, 400 gig and 800 gig, the beginning of next year. So that'll be the external launch. Internally, we already have solutions qualified. So if you're interested in transceivers that we talked about today, just reach out to your local Siemon salesperson. And again, we can work out a solution specific for your deployment needs.
Thanks, Ryan. Just 2 more questions. Does Siemon do cable bundles to support AI systems?
So that's a good question. I was showing that today we do bundles for fiber optic cables out of our Mexico factory. We can also do that for copper as well, but again, every system is different, as I was describing, and so you would just have to, again, reach out to your local sales representative, and we can make a solution specific to your needs.
Thanks, Ryan. And final question, are there other areas in your network for improving efficiency outside of what was discussed today?
So the GPU connections, again, are the highest volume. They're also the highest power connections, and they add up quickly. But there's other parts of the network as well that can benefit from efficient cabling options, like the storage network and also the front end network as well. It doesn't have as many connections, so it doesn't add up as quickly for savings. But you can basically use efficient cabling best practices across any part of your network.
Excellent. Thank you, Ryan. Yeah, that's all the questions I see. Any closing comments before I close us out here, Ryan?
No, so I think we went over everything. Again, we're going to be at the Open Compute Project Summit in a couple weeks. We'll be working with Dell and Keysight and showing Dell solutions and Keysight solutions with Siemon cabling. And if you're in town, I look forward to seeing you.
Excellent. Thanks, Ryan. So yeah, before we close the session, I'd like to say a huge thank you to everyone who was able to join us today, and to Ryan for his time and excellent insights. Our next Tech Talk webinar will be in November 12th, and the topic will focus on optical cabling strategies for high-performance 400, 800G AI deployments. And Siemon is partnering with NVIDIA on that one, so you don't want to miss it. If you would like any additional information on how Siemon can support your data center projects, please reach out to Ryan directly or contact your local Siemon representative today. Thanks again, everyone, and enjoy the rest of your day.
Thank you.